December 20th, 1943, 30,000 feet above the frozen landscape of northern Germany. The morning sky stretches endlessly, painted in shades of steel and ice. Luftwaffe Oberleutnant Franz Stigler pulls his Messerschmitt Bf 109 into a climbing turn, his breath visible in the frigid cockpit air despite his heated flying suit. Through his gun sight, a massive four-engine bomber materializes from the scattered cloud cover. A Boeing B-17 Flying Fortress, its olive-drab paint scheme stark against the winter sky. But this is no ordinary encounter. The American bomber flies with its tail section nearly severed, gaping holes torn through its fuselage like jagged wounds. Its number 2 engine trails black smoke, the propeller feathered and motionless. Wing panels flap loosely in the slipstream, and the rear gunner's position hangs empty, the plexiglass shattered and stained with blood. Yet impossibly, the Flying Fortress continues its steady course westward. Its remaining 3 engines maintain their rhythmic thunder. The aircraft holds formation discipline, its flight surfaces responding smoothly to control inputs from pilots who should be dead or dying. Stigler stares in disbelief as what appears to be a flying wreck demonstrates the impossible, continuing to fly, continuing to fight, continuing to survive damage that should have sent it spiraling into the German countryside below. This moment would define a new understanding of what American bombers could endure and why German pilots began to whisper of aircraft that seemed to repair themselves in flight. By late 1943, the air war over Europe had reached a deadly crescendo. The United States Army Air Forces had committed to a strategy of daylight precision bombing, sending hundreds of heavy bombers deep into the heart of Nazi Germany. The theory seemed sound on paper: massive formations of heavily armed flying fortresses. SEs and liberators would overwhelm German defenses through sheer firepower and numbers, delivering devastating blows to the Reich's industrial capacity. The reality proved far more brutal. German fighter pilots, battle-hardened veterans of years of aerial combat, had developed increasingly sophisticated tactics to counter the American bomber streams. They concentrated their attacks on the most vulnerable positions, targeting engines, fuel systems, and crew compartments with devastating efficiency. The Luftwaffe's experienced aces knew exactly where to strike for maximum effect, and their cannon-armed fighters packed enough firepower to tear apart even the sturdiest aircraft. German ground controllers had perfected an early warning system that could track incoming bomber formations from hundreds of miles away. Fighter squadrons would mass at predetermined intercept points, launching coordinated attacks that could destroy entire bomber groups within minutes. The mathematics seemed to favor the defenders. Each German fighter pilot needed only to down a single bomber to achieve a favorable exchange rate, while American bomber crews faced the daunting prospect of flying 25 missions over increasingly hostile territory. The human cost mounted relentlessly. American bomber crews understood the grim statistics all too well. The average life expectancy of a B-17 crew member hovered around 11 missions. Men barely out of their teens found themselves manning defensive gun positions in aircraft flying straight and level through murderous crosswinds of flak and cannon fire. The psychological pressure was immense, knowing that mathematical probability suggested few would survive their required tour of duty. German pilots initially viewed the American bombing campaign with professional confidence. Their fighter aircraft possessed superior performance characteristics in terms of speed, climb rate, and maneuverability. Their pilots averaged significantly more flight hours and combat experience than their American counterparts. The rigid bomber formations appeared to offer perfect targets for experienced fighter pilots who could exploit gaps in defensive fire coverage. Yet something unexpected began to emerge from these deadly encounters. American bombers that should have fallen from the sky continued flying. Aircraft with engines destroyed, control surfaces damaged, and crew members wounded somehow maintained formation discipline and reached friendly territory. German pilots found themselves expending increasingly large amounts of ammunition to achieve kills that had previously required only brief firing passes. The phenomenon defied conventional understanding of aircraft vulnerability. Luftwaffe intelligence officers struggled to explain reports from their most reliable pilots describing bombers that absorbed incredible amounts of battle damage yet continued operating effectively. These aircraft seemed to possess an almost supernatural ability to continue functioning despite catastrophic structural damage that would have downed any German aircraft immediately. Fighter pilots began to report encounters with bombers displaying apparent mechanical self-repair capabilities during flight. Fuel leaks would mysteriously stop flowing, engine fires would extinguish themselves without crew intervention. Aircraft with severely damaged control surfaces would somehow regain stable flight characteristics. These reports initially faced skepticism from higher command levels, dismissed as combat stress or misidentification under the extreme conditions of aerial combat. The mounting evidence, however, could not be ignored indefinitely. Too many experienced pilots were reporting similar phenomena for the accounts to be dismissed as imagination or propaganda. The development of American heavy bomber technology had followed a distinctly different philosophical approach than European aircraft design. While German and British designers prioritized performance parameters like speed and altitude capability, American engineers focused obsessively on survivability and operational reliability. This fundamental difference in design philosophy would prove decisive in the brutal arithmetic of strategic bombing campaigns. Boeing's design team, led by Chief Engineer Wellwood Beale, had incorporated unprecedented levels of structural redundancy into the B-17 Flying Fortress from its earliest development phases. The aircraft featured multiple backup systems for every critical function, from flight controls to electrical power generation. If one system failed, secondary and tertiary systems would automatically assume the workload, maintaining aircraft functionality even under extreme battle damage conditions. The B-17's control system exemplified this redundancy philosophy. Traditional aircraft relied on single cable runs connecting cockpit controls to flight surfaces. The Flying Fortress employed multiple parallel cable systems with automatic tension adjustment mechanisms. If enemy fire severed primary control cables, backup systems would immediately engage, maintaining pilot control authority. This system proved so effective that B-17s could continue flying with up to 70% of their control cables destroyed. Self-sealing fuel tank technology represented perhaps the most revolutionary advancement in bomber survivability. Developed by American chemical engineers working with rubber companies, these tanks featured multiple layers of specialized materials that would automatically seal punctures when exposed to aviation fuel. The innermost layer consisted of vulcanized rubber that would swell and seal holes within seconds of being penetrated. An intermediate layer provided structural support, while the outer layer offered protection against fragment damage. The psychological impact of this technology on German pilots cannot be overstated. Luftwaffe fighters had traditionally targeted fuel systems as the most effective means of achieving quick kills. Incendiary ammunition would ignite fuel vapors, causing spectacular explosions that destroyed bombers instantly. American self-sealing tanks frustrated this proven tactic, requiring German pilots to sustain longer firing passes while exposing themselves to defensive fire from bomber gunners. Advanced autopilot systems provided another layer of apparent self-repair capability. The B-17's automatic flight control equipment, manufactured by the Bendix Corporation, could maintain stable flight even when human pilots were wounded or killed. This system interfaced directly with the Norden bomb site, allowing the bombardier to control aircraft flight path during bombing runs with unprecedented precision. More importantly for survivability, the autopilot could compensate for asymmetric thrust conditions, structural damage, and control surface irregularities that would overwhelm human pilots under combat stress. Boeing engineers had also designed the B-17's electrical system with extraordinary fault tolerance. Multiple engine-driven generators provided redundant power sources with automatic switching systems that would route electrical current around damaged components. Battery backup systems could maintain critical flight instruments and radio equipment for extended periods even with total generator failure. This electrical redundancy ensured that vital aircraft systems continued operating regardless of battle damage severity. The structural design philosophy behind American bombers emphasized damage tolerance rather than damage avoidance. While German aircraft featured efficient but vulnerable designs that could be disabled by relatively minor battle damage, American bombers incorporated massive structural safety margins. Wing spars were over-engineered to withstand loads far exceeding normal operational requirements. Fuselage frames featured redundant load paths that could redistribute stresses around damaged sections. This approach to bomber design reflected broader American industrial capabilities and strategic thinking. The United States possessed the manufacturing capacity and raw materials to build aircraft with extensive redundant systems, even if this approach resulted in heavier, less efficient aircraft. German industry, constrained by resource limitations and competing military priorities, could not afford such luxuries in their aircraft designs. The cumulative effect of these technological advantages created aircraft that appeared almost invulnerable to German pilots accustomed to more conventional aircraft vulnerabilities. American bombers seemed to possess an almost magical ability to absorb punishment and continue flying, leading to widespread rumors among Luftwaffe pilots about American secret weapons or supernatural aircraft capabilities. From the cramp, Ed cockpit of his Messerschmitt Bf-109, Hauptmann Egon Meyer had witnessed the evolution of American bomber tactics firsthand. A seasoned fighter pilot with over 100 confirmed victories, Meyer possessed an intimate understanding of aircraft vulnerability points developed through years of aerial combat. Yet the flying fortresses presented challenges that defied his accumulated expertise and instincts. Traditional fighter tactics relied on precise targeting of critical aircraft systems. A short burst into an engine cowling would typically destroy the power plant and force an immediate landing or bailout. Fuel system hits would create spectacular fireballs that eliminated bombers within seconds. Control surface damage would render aircraft uncontrollable, sending them into fatal spins or dives. These proven techniques had served German pilots well against British bombers and earlier American aircraft types. The B-17s, however, seemed to absorb this punishment and continue flying as if nothing had happened. Meyer watched in frustration as his carefully aimed cannon bursts tore visible chunks from bomber wings and fuselages without producing the expected results. Engines continued running despite obvious battle damage. Aircraft maintained formation discipline even with gaping holes in their control surfaces. Most unsettling of all, bombers that should have been streaming fuel and fire somehow sealed their wounds and continued toward their targets. German pilots began to develop superstitious explanations for these phenomena. Some claimed that American bombers were constructed from special materials that could regenerate like living tissue. Others suggested that the aircraft contained secret technological systems beyond German understanding. The most persistent rumor involved American crews using supernatural or occult methods to protect their aircraft during combat missions. These explanations, while scientifically absurd, reflected the genuine psychological impact of encountering aircraft that violated every assumption about aerial combat. Fighter pilots who had achieved remarkable success against conventional aircraft found themselves expending enormous amounts of ammunition against bombers that seemed impervious to damage. The confidence and aggressive spirit that characterized successful fighter pilots began to erode under the strain of repeated encounters with seemingly invulnerable opponents. Tactical formations employed by American bomber groups amplified the defensive effectiveness of individual aircraft redundant systems. The combat box formation positioned bombers to provide mutual defensive fire coverage while minimizing exposure to fighter attacks. Each bomber could bring multiple gun positions to bear on attacking fighters, creating interlocking fields of fire that forced German pilots to approach through concentrated defensive fire zones. The sight of a typical American bomber formation approaching a target presented a formidable spectacle that German pilots learned to respect and fear. Hundreds of four-engine aircraft flying in precise geometric patterns, each bristling with defensive armament and protected by layers of escort fighters. The formation seemed to pulse with mechanical life as gun turrets tracked potential threats and engines maintained their steady, ominous rhythm. Fighter pilots developed increasingly desperate tactics to counter these formations. Head-on attacks maximized the relative closing speed and minimized exposure time to defensive fire, but required split-second timing and enormous courage to execute effectively. Attacking from below exploited the traditional blind spot in bomber defensive coverage, but exposed fighters to concentrated fire from multiple aircraft simultaneously. The most successful German pilots learned to target specific vulnerable points that could disable bomber systems despite their redundancy. The cockpit area remained vulnerable to precise cannon fire that could eliminate the human element necessary for aircraft operation. Wing root areas, where fuel lines and control cables concentrated, offered high-value targets for pilots skilled enough to hit such small areas during high-speed attack passes. Yet even these refined tactics often failed to produce decisive results against American bombers equipped with advanced damage control systems. Aircraft that absorbed seemingly fatal damage would somehow recover and continue flying, leaving German pilots to wonder if their attacks had achieved any meaningful effect whatsoever. The technological sophistication of American bomber defensive systems represented a quantum leap in aircraft survivability engineering. Beyond the visible gun turrets and armor plating, flying fortresses incorporated numerous hidden systems designed to maintain functionality under combat damage conditions that would destroy conventional aircraft. Self-sealing fuel tanks employed multiple layers of specialized materials engineered to react chemically with aviation gasoline. When projectiles penetrated these tanks, the escaping fuel would cause rubber compounds to swell and seal the puncture within seconds. This technology eliminated the traditional vulnerability that German fighters had exploited successfully against earlier bomber types, fundamentally altering the tactical equation of aerial combat. The tank construction involved carefully engineered laminated layers, each serving specific functions in the sealing process. The innermost layer consisted of fuel-resistant rubber compounds that maintained flexibility under extreme temperature conditions. Intermediate layers provided structural support and it contained chemical compounds that would react with fuel to accelerate the sealing process. The outermost layer offered protection against fragmentation damage and contained fire-retardant materials that would help prevent fuel ignition even during the sealing process. Advanced electrical systems provided another layer of apparent self-repair capability that mystified German pilots and intelligence analysts. Multiple engine-driven generators supplied redundant electrical power, with automatic switching systems that could instantly reroute power around damaged components. If battle damage destroyed primary electrical systems, backup systems would seamlessly assume the workload without interrupting critical aircraft functions. The B-17's autopilot system, manufactured by Bendix Corporation, represented cutting-edge technology that few German pilots fully understood. This system could maintain stable flight under conditions that would overwhelm human pilots, automatically compensating for engine failures, control surface damage, and asymmetric loading conditions. The autopilot interfaced with the aircraft's gyroscopic flight instruments and could maintain precise heading and altitude control even when human crew members were wounded or incapacitated. Leadership decisions at the highest levels of American military hierarchy had prioritized bomber survivability over traditional performance parameters like speed or payload capacity. General Henry Hap Arnold and his strategic planning staff understood that bomber crews represented irreplaceable assets requiring years of training to develop. Losing experienced crews meant losing the institutional knowledge and combat expertise necessary for successful strategic bombing campaigns. This philosophy contrasted sharply with German approaches to aircraft design, which emphasized performance efficiency and resource conservation. German industry, operating under severe material constraints and competing military priorities, could not afford the luxury of over-engineering aircraft with extensive redundant systems. The result was a fundamental mismatch between German expectations of aircraft vulnerability and American bomber reality. Enemy adaptation to American bomber capabilities followed predictable patterns as German pilots developed new tactics to counter the apparent invulnerability of flying fortresses. Luftwaffe research units conducted detailed analysis of captured bomber wreckage, attempting to understand the technological systems that provided such remarkable survivability. Intelligence reports described American aircraft as incorporating known materials and mysterious mechanical systems that could repair battle damage automatically. German weapons development programs began focusing on specialized ammunition designed to defeat American self-sealing fuel systems and redundant electrical circuits. Incendiary rounds were modified with delayed action fuses that would allow projectiles to penetrate deeply into fuel tanks before igniting, potentially overwhelming the sealing mechanisms. High-explosive rounds were designed to create multiple simultaneous punctures that might exceed the repair capacity of self-sealing systems. The psychological impact on German aircrews extended beyond individual pilot morale to affect overall Luftwaffe operational effectiveness. Fighter squadrons that had previously achieved decisive tactical victories found themselves engaged in prolonged battles of attrition against bomber formations that seemed capable of absorbing unlimited punishment. The confident aggression that characterized successful fighter pilots began to give way to cautious tactics focused on survival rather than decisive engagement. This shift in mindset represented a strategic victory for American bomber advocates who had argued that heavily defended aircraft could penetrate German airspace and deliver decisive blows against industrial targets. The apparent invulnerability of American bombers to conventional fighter attacks validated the concept of daylight precision bombing and justified the enormous resources invested in developing and deploying these remarkable aircraft. The morning of October 14, 1943, would forever be remembered as Black Thursday in the annals of American bomber operations, yet it also marked the moment when German pilots fully comprehended the extraordinary capabilities of American aircraft systems. The target was Schweinfurt, home to Germany's vital ball-bearing production facilities, and the mission would demonstrate both the vulnerability and the remarkable resilience of flying fortresses under the most extreme combat conditions. As the massive bomber formation approached German airspace, Luftwaffe fighters rose to meet them in unprecedented numbers. Nearly 400 German fighters had been assembled for this crucial defensive mission, representing the largest concentration of fighter aircraft the Luftwaffe had ever deployed against a single bomber formation. The stage was set for a decisive test of American bomber survivability against overwhelming odds. The first attacks began over the German border, with waves of Messerschmitt Bf-109s and Focke-Wulf 190s launching coordinated assaults against the bomber formations. German pilots employed every tactical innovation developed through months of bitter experience, concentrating their attacks on apparent weak points in the American defensive formations. Yet even under this unprecedented assault, individual bombers continued to demonstrate their remarkable ability to absorb punishment and maintain formation discipline. One B-17, piloted by Lieutenant Robert Rosenthal, absorbed direct hits from multiple cannon shells that destroyed its No. 2 engine and severely damaged the wing structure. Fuel streamed from punctured tanks, creating visible vapor trails that should have ignited under the intense combat conditions. Yet the aircraft's self-sealing systems functioned as designed, automatically sealing the fuel leaks within minutes while the crew maintained their position in the bomber formation. Another flying fortress, flown by Captain Robert Morgan, sustained damage that severed primary flight control cables and destroyed much of the aircraft's tail section. Under conventional circumstances, such damage would have rendered the aircraft uncontrollable, sending it into a fatal spin or dive. Instead, the B-17's redundant control systems automatically compensated for the damage, allowing the crew to maintain formation discipline and continue toward their target despite flying what appeared to be a mortally wounded aircraft. The most remarkable incident involved a bomber piloted by Second Lieutenant Charlie Brown, whose aircraft absorbed an extraordinary amount of battle damage yet continued flying through what can only be described as mechanical determination enhanced by superior engineering. The B-17 had been attacked repeatedly by German fighters, suffering damage to engines, fuel systems, control surfaces, and crew compartments. Several crew members had been wounded, and the aircraft appeared to be flying on mechanical instinct rather than human control. Franz Stigler, the German pilot who encountered Brown's crippled bomber, later described the aircraft as resembling a flying coffin that refused to die. The bomber's engines continued running despite visible battle damage. Its fuel systems had somehow sealed themselves after being punctured multiple times, and the aircraft maintained stable flight despite gaping holes in its control surfaces. Most remarkably, the bomber's electrical systems continued functioning, powering critical flight instruments and radio equipment that allowed the crew to navigate toward friendly territory. German pilots observing these encounters began to report that American bombers possessed capabilities that defied rational explanation. Aircraft that absorbed dozens of cannon hits continued flying as if protected by supernatural forces. Fuel systems that should have erupted in spectacular fireballs somehow sealed themselves and continued operating normally. Control systems that suffered catastrophic damage continued responding to pilot inputs with mechanical precision that seemed impossible under the circumstances. The psychological impact of these observations spread rapidly through German fighter squadrons. Pilots who had achieved remarkable success against conventional aircraft began to question their tactical approaches and weapons' effectiveness. The confident aggression that characterized successful fighter operations gave way to more cautious tactics as pilots realized that American bombers could not be destroyed using conventional methods. Intelligence reports reaching German high command described American aircraft as incorporating unknown technological systems that provided capabilities beyond German understanding. Some reports suggested that American bombers contained self-repairing mechanisms that could automatically seal battle damage and restore aircraft functionality during flight. Other reports speculated about advanced materials that could regenerate after being damaged, similar to biological healing processes. These reports, while scientifically inaccurate, reflected the genuine bewilderment of experienced German pilots encountering aircraft that violated every assumption about aerial combat vulnerabilities. The systematic over-engineering of American bomber systems had created aircraft that appeared to possess almost magical survival capabilities to observers unfamiliar with the underlying technological principles. The cumulative psychological Impact of these encounters fundamentally altered German tactical doctrine and pilot psychology in ways that would prove decisive for the remainder of the war. Fighter pilots who had previously approached bomber formations with confidence and aggressive tactics began to exhibit more cautious behavior that reduced their overall effectiveness against American operations. Luftwaffe training programs attempted to address the apparent invulnerability of American bombers by developing specialized attack techniques designed to overcome their defensive systems. Pilots received instruction in targeting specific vulnerable points that might bypass the redundant systems protecting critical aircraft functions. These techniques required extraordinary precision and exposed attacking fighters to concentrated defensive fire for extended periods, resulting in increased German pilot casualties without proportionally increased bomber losses. The most experienced German aces began to develop superstitious behaviors and explanations for their encounters with apparently invulnerable American aircraft. Some pilots carried personal talismans or performed ritual behaviors before engaging bomber formations, believing that supernatural forces protected American aircraft from conventional weapons. Others developed elaborate theories about secret American technologies or materials that provided capabilities beyond German scientific understanding. Major Walter Nowotny, one of Germany's highest-scoring fighter aces, documented his growing frustration with American bomber encounters in personal letters and official reports. Despite his exceptional skill and experience, Nowotny found himself expending enormous amounts of ammunition against bombers that seemed impervious to damage. His typical brief firing passes, which had proven devastatingly effective against other aircraft types, produced minimal results against flying fortresses equipped with self-sealing fuel systems and redundant control mechanisms. The strategic implications of these tactical developments extended far beyond individual combat encounters. German fighter squadrons that had previously achieved decisive tactical victories found themselves engaged in prolonged battles of attrition that favored the numerically superior American forces. The apparent invulnerability of individual bombers meant that German pilots needed to sustain longer attacks while exposing themselves to increasingly effective American defensive fire. Luftwaffe maintenance crews reported dramatic increases in ammunition consumption without corresponding increases in confirmed bomber kills. Fighter aircraft returned from missions with empty ammunition bays and frustrated pilots who described hitting bombers repeatedly without achieving decisive results. This ammunition shortage became increasingly critical as German industrial capacity struggled to meet the demands of prolonged aerial combat against apparently invulnerable opponents. The morale impact on German ground crews and support personnel matched the psychological pressure experienced by fighter pilots. Mechanics and armorers who had previously sent pilots into combat with confidence in their aircraft and weapons began to question whether German equipment could effectively counter American technological advantages. Reporto. Teas of bombers that seemed to repair themselves during flight challenged fundamental assumptions about mechanical systems and aircraft vulnerability. German propaganda efforts attempted to counter these morale problems by describing American bomber losses in exaggerated terms while minimizing references to aircraft that survived apparently fatal damage. However, frontline personnel could not ignore the evidence of their own experiences with bombers that continued flying despite absorbing punishment that should have destroyed them immediately. The tactical innovations developed by German pilots in response to American bomber capabilities represented some of the most creative and desperate measures in the history of aerial combat. Fighter pilots began employing ramming attacks as a last resort against bombers that seemed immune to conventional weapons. These kamikaze-style tactics achieved limited success while consuming irreplaceable experienced pilots at an unsustainable rate. Some German squadrons experimented with coordinated attacks using multiple fighters to concentrate firepower against individual bombers, hoping to overwhelm their defensive systems through sheer volume of fire. While these tactics occasionally succeeded, they required precise coordination and timing that proved difficult to achieve under combat conditions while exposing multiple fighters to defensive fire simultaneously. The most significant strategic impact involved the gradual shift in German defensive priorities from offensive fighter operations to more defensive tactics focused on survival rather than decisive engagement. This fundamental change in tactical philosophy reflected the recognition that American bombers possessed capabilities that could not be countered using conventional methods, forcing German air defenses into an increasingly reactive posture that would prove decisive in the final outcome of the air war. The statistical analysis of bomber survivability rates revealed the full extent of American technological achievements in aircraft design and engineering. By early 1944, detailed examination of mission reports and battle damage assessments demonstrated that B-17 flying fortresses were returning from combat missions with damage levels that would have destroyed any previous aircraft type. The numbers told a remarkable story of engineering triumph over the brutal mathematics of aerial warfare. Combat loss rates for American heavy bombers decreased significantly as crews and aircraft gained operational experience despite intensifying German defensive efforts. Initial missions in 1943 had resulted in catastrophic losses approaching 20% of participating aircraft. By mid-1944, loss rates had decreased to less than 4%, despite German deployment of increasingly sophisticated fighter tactics and weapons systems designed specifically to counter American bomber capabilities. Battle damage reports documented aircraft returning to base with hundreds of bullet and cannon holes, destroyed engines, severed control cables, and punctured fuel systems that had somehow sealed themselves during flight. Maintenance crews developed specialized repair procedures for damage types that had never been encountered in previous aircraft operations. The sheer variety and extent of battle damage that flying fortresses could survive exceeded the imagination of pre-war aircraft designers. One particularly well-documented case involved a B-17 that returned to base after losing its entire tailgunner position to a direct cannon hit, suffering multiple fuel system punctures, and flying the final 2 hours of its mission on only 2 operational engines. Post-flight inspection revealed that the aircraft's self-sealing fuel systems had automatically sealed 17 separate punctures in various fuel tanks, while redundant electrical systems had maintained power to critical flight instruments despite extensive wiring damage throughout the aircraft. German countermeasures evolved in response to American bomber survivability, but these adaptations often proved inadequate against the systematic over-engineering of flying fortress defensive systems. Luftwaffe weapons development programs produce specialized ammunition designed to defeat self-sealing fuel tanks and redundant electrical systems, including delayed-action incendiary rounds and high-explosive projectiles with enhanced fragmentation effects. The most significant German innovation involved the development of air-to-air rockets designed to destroy bomber formations through proximity explosions rather than direct hits. These weapons, designated R4M Orkan rockets, could theoretically overwhelm bomber defensive systems through massive explosive force that would destroy aircraft regardless of their redundant safety systems. However, the rockets proved difficult to aim accurately and were deployed too late in the war to significantly impact overall bomber survivability statistics. Intelligence analysis conducted by both German and American forces revealed the extent to which bomber survivability affected overall strategic bombing effectiveness. German industrial surveys indicated that bombing accuracy improved significantly as bomber crews gained confidence in their aircraft's ability to survive battle damage and continue to target despite intense defensive fire. This increased accuracy compensated for the reduced bomb loads necessary to accommodate the weight of defensive systems and redundant equipment. The psychological impact on German civilian populations became increasingly significant as apparently invulnerable American bombers continued to appear over German cities despite massive defensive efforts. The sight of bomber formations that seemed immune to fighter attacks and anti-aircraft fire created a sense of hopelessness among German civilians who had initially believed their air defenses could protect them from strategic bombing. German pilot training programs struggled to adapt to the realities of combat against aircraft that violated traditional assumptions about aerial warfare. New pilots arriving at operational squadrons received instruction in attacking tactics that had proven effective against conventional aircraft, only to discover that these techniques produced minimal results against Americans. Can bombers equipped with advanced defensive systems? The attrition rate among experienced German fighter pilots accelerated as prolonged engagements with bomber formations exposed them to concentrated defensive fire for extended periods. Luftwaffe squadrons that had previously rotated experienced pilots into training roles found themselves unable to spare veterans for instruction duties, leading to declining training quality and reduced effectiveness among replacement pilots. Manufacturing priorities within German industry shifted toward producing larger quantities of conventional fighters and ammunition, rather than developing advanced aircraft that could potentially counter American bomber capabilities. This decision reflected resource constraints and competing military priorities, but also represented an implicit acknowledgement that German technology could not match American achievements in aircraft survivability engineering. The strategic bombing campaign's success increasingly depended on the psychological impact of apparently invulnerable bomber formations, rather than purely physical destruction of industrial targets. German workers in targeted industries began to exhibit decreased productivity and increased absenteeism as they witnessed repeated bomber attacks that seemed impossible to prevent or counter effectively. The long-term implications of American bomber survivability extended far beyond the immediate tactical advantages gained in combat operations. The technological innovations developed for wartime aircraft would fundamentally reshape post-war aviation design philosophy and establish engineering principles that continue to influence aircraft development today. Self-sealing fuel tank technology, initially developed for military bombers, became standard equipment in civilian aircraft operating in potentially hazardous environments. Commercial aviation adopted these systems for aircraft operating over water or in regions where emergency landing sites were unavailable, significantly improving passenger safety during the rapid expansion of international air travel in the post-war era. The redundant electrical and control systems pioneered in Flying Fortress design established engineering principles that would prove essential for the development of jet aircraft and modern airliner systems. Multiple backup systems for critical aircraft functions became standard practice in commercial aviation, contributing to the remarkable safety record achieved by modern airline operations through systematic elimination of single-point failure modes. Advanced autopilot technology developed for bomber operations provided the foundation for modern flight management systems that enable precise navigation and fuel-efficient flight operations. The integration of autopilot systems with navigation equipment, first demonstrated in the B-17's interface with the Norden bombsight, established design principles that continue to evolve in contemporary aircraft automation systems. The industrial capacity and engineering expertise developed for bomber production contributed significantly to American dominance in post-war aerospace industries. Companies like Boeing leveraged their wartime experience with complex aircraft systems to develop successful commercial airliner designs that established American manufacturers as global leaders in aviation technology. European aircraft manufacturers struggled to match American achievements in systems integration and redundancy engineering during the immediate post-war period. The technological gap created by American BOOs. Amber development programs contributed to the competitive advantages that allowed American companies to dominate international aircraft markets for decades following the war's conclusion. Military aviation doctrine incorporated lessons learned from bomber survivability studies into the design requirements for subsequent aircraft generations. The emphasis on damage tolerance and system redundancy became fundamental principles in military aircraft specification development, influencing everything from fighter design to transport aircraft engineering throughout the Cold War era. The psychological impact of American bomber survivability on German military thinking extended beyond aviation into broader strategic planning and weapon system development. German engineers and military planners developed a lasting respect for American technological capabilities that influenced post-war defense planning and international relations throughout the Reconstruction period. Academic institutions established research programs focused on aircraft survivability engineering, drawing upon wartime experience with bomber defensive systems to develop theoretical frameworks for understanding aircraft vulnerability and protection mechanisms. These research programs contributed to advances in materials science, structural engineering, and systems design that benefited both military and civilian applications. The documentation and analysis of bomber battle damage provided unprecedented data for understanding aircraft structural behavior under extreme conditions. This information proved invaluable for developing computer modeling techniques and testing procedures that enabled more efficient aircraft design processes in subsequent decades. International aviation safety standards incorporated principles derived from American bomber survivability studies, establishing requirements for redundant systems and damage tolerance that became universal standards for aircraft certification. The influence of wartime bomber technology can be traced through decades of regulatory development that continues to shape contemporary aircraft design requirements. The strategic implications of bomber survivability for post-war military planning extended beyond aviation into broader questions of weapons effectiveness and defensive capabilities. The apparent inability of conventional weapons to reliably counter well-designed aircraft systems influenced military thinking about future warfare scenarios and the development of more sophisticated weapons systems. Cultural memory of American bomber achievements contributed to enduring perceptions of American technological superiority that influenced international relations and defense cooperation agreements throughout the Cold War period. The image of apparently invulnerable flying fortresses continuing to fly despite catastrophic battle damage became a symbol of American industrial capability and engineering excellence that resonated far beyond military aviation circles. The remarkable story of American bombers that seemed to repair themselves during flight represents more than a fascinating chapter in aviation history. It embodies a fundamental shift in engineering philosophy that prioritized human survival and mission completion over traditional performance metrics like speed or efficiency. The systematic over-engineering of flying fortress defensive systems demonstrated that apparent technological magic often results from methodical application of sound engineering principles and generous safety margins. The German pilots who witnessed these seemingly impossible aircraft capabilities were observing the practical results of American industrial capacity applied to a specific engineering challenge. The self-sealing fuel tanks, redundant control systems, and automated flight equipment that created the illusion of self-repairing aircraft represented thousands of hours of research and development by teams of engineers who understood that crew survival was paramount to mission success. This design philosophy would prove prophetic in its influence on subsequent aviation development. Modern commercial aircraft incorporate multiple layers of redundant systems, damage-tolerant structures, and automated emergency procedures that trace their conceptual origins to the Flying Fortress design team's innovative approaches to aircraft survivability. The principle that aircraft should be capable of continued safe operation despite significant system failures has become fundamental to contemporary aviation safety standards. The psychological impact of these technological achievements extended far beyond their immediate tactical applications. The sight of apparently invulnerable bombers continuing to fly despite catastrophic damage represented a powerful demonstration of industrial capability and engineering excellence that influenced international perceptions of American technological leadership. This reputation for innovation and reliability would prove valuable in post-war international relations and commercial competition. Perhaps most significantly, the story illustrates how technological superiority can emerge from systematic application of abundant resources rather than revolutionary breakthroughs. The Americans did not invent fundamentally new technologies so much as they applied existing knowledge with unprecedented thoroughness and generous safety margins. The result was aircraft that seemed to possess magical capabilities to observers unfamiliar with the underlying engineering principles. The legacy of these remarkable aircraft continues to influence aviation development today, reminding us that apparent miracles often result from methodical engineering excellence and unwavering commitment to human survival above all other considerations.